another example of finding the directional derivative at a specific point in a specific angular direction. So we have our function fxy equals xe to the minus 2y, and we're going to go ahead and evaluate that at the point 5, 0. So we're going to find the directional derivative in that direction, in the direction of pi halves, or 90 degrees. So you remember that we're going to find the derivative of this thing, the directional derivative, and what we need to do first is we need to find the directional derivative at both of the points. So we're going to find f sub x, and f sub x is really easy. That's just going to be e to the minus 2y, all right, since the derivative with respect to x is 1, and fy is a chain rule, all right, so that's going to be x e to the minus 2y, since the derivative of e is e, but then the derivative of this negative 2y with respect to y is negative 2. And then we're going to evaluate both of these at the point 5, 0. Pretty easy. When we do that, substitute 0 back in for y. E to the minus 2 times 0 is going to be 1, so that's nice and easy. And then finally, we're going to have negative 2 times 5 times e to the minus 2 times 0, which is negative 10. Now we're going to have our formula, all right, and our formula for du of f at, in this case, 5, 0, is going to be 1 times the cosine of pi halves plus negative 10 times sine at pi halves. Right? We know cosine of pi halves is 0. We know that sine at pi halves is 1. And by using advanced numerical methods, 10 times, or negative 10 times 1 is negative 10. And remember what that represents. That represents the rate of change at the point 5, 0 in the direction of pi halves. All right, so essentially what's happening is we're almost going straight down at that point. All right, and that makes sense because e to the minus 2y is probably getting really close to 0 at that point. All right, the rate of change is going to be extremely small, or extremely downward at that point, because that e to the minus 10 is an extremely large value. So let's consider a different type of directional derivative. Let's say this time, instead of an angle, we're looking at a vector direction. And just to give you an idea of what that looks like, let's say we have a function in 3 dimensions, and let's just consider it to be like almost like a downward hill. All right, so this is our function f, and let's just have this point right here. Let's call that p. And what we're looking for is we're looking for the directional derivative in a specific direction. All right, so now we're not looking at this example specifically, so for right now, take this out of your mind. We're not even looking at that example, but just an overview as to what we're looking at. There's a number of different vectors that are essentially not necessarily normal, but are going to be tangent to the plane or jettisoning from the plane in a specific direction. So for example, we could have one that does something like this, and I could call that like u sub 1 vector, or we could have another vector, maybe just does something like that. I could call that u sub 2, and we could do this all day, right? There's an infinite number of vectors that we can use. All right, so we could have like almost like a perpendicular. We could call that u3. All right, we could even have one in the opposite direction if we really wanted to. All right, so let's call this animal maybe something like this, where it's going against the natural slope. So we call that u4. All right, and just assume that each of those is a unit vector. All right, that's what we're looking for. We're looking for the rate of change in the specific direction, okay, of that unit vector. And so remember, we had a formula earlier that all we're going to do is we're going to find a unit vector, and then we're going to multiply that by each of the derivatives with respect to x and y at the given point. All right, so it's actually not going to be too bad to do this. All right, so let's take a look at a couple examples as to how to implement this. So we have our first one, which is going to be the function fx over y at the point 6, negative 2, and the vector v is negative 1, 3. The first thing we have to do is we have to find a unit vector in the same direction. Okay, this is not a unit vector. Okay. So remember, to find a unit vector, it's v over magnitude v. All right, so the magnitude of v is going to be equal to the square root of -1 squared plus 3 squared, otherwise known as root 10. And so our unit vector in the same direction is going to be -1 over root 10, comma 3 over root 10. And in this example, those are going to be our a and our b. And we're going to multiply those by the derivatives. Fx at 6, -2, Fy at 6, -2. All right. Now let's find those derivatives. And to start, what we should probably do is rewrite this, just like we were in Calc 1, rewriting things all the time that had denominators. We just want to make that a negative exponent. And let's find Fx. All right, Fx is really easy. That's just going to be y to the -1. And then Fy is not too bad. That's going to be opposite of x, y to the -2. And we're going to evaluate each of those at the points 6, -2. So that's the point, thinking back to our curve, that we're trying to find the directional derivative of. Right? So Fx is going to be -2 to the -1, otherwise known as -1/2. And Fy is going to be the opposite of 6 times -2 to the -2. And that's going to be -6 over +4, or -3/2. And then finally, what we can do is we can substitute these back in, and we can just multiply each of these by the unit vector's direction, so the I and the j. And so our formula that we have, so d sub u at f of 6, -2 is going to be equal to, so we had -1 over root 10. We're going to multiply that by -1/2. And then we also have this 3 over root 10 times -3 over 2. All right, and this can actually be simplified a little bit. So that's going to wind up being +1. And then the other numerator is going to be a -9. If we multiply, we both get 2 roots of 10 in both of the denominators. And so this is going to work out to be -8 over 2 roots of 10, otherwise known as -4 over root 10. If we wanted to rationalize it, we can by multiplying by root 10 over root 10. So we could get 4 roots of 10 over 10, or even more simple, 2 roots of 10 over 5. And that's just our directional derivative. All right, that just tells us the rate of change at the point 6, -2 in a specific direction. All right, and the direction is going to be the vector's direction, all right, of -1, 3. It doesn't necessarily matter the magnitude of the vector, because remember, we're finding a unit vector. All right, so that just means that it's going to be a magnitude of 1 no matter what. So it's not really affecting the magnitude or the intensity of the slope. One final example. All right, same sort of idea. We have this function e to the -x sine y. We have our point 0 pi thirds, and we have our vector 3i minus 2j. So our unit vector is going to be, first of all, magnitude v is going to be equal to the square root of 3 squared plus -2 squared, otherwise known as root 13. That means that the unit vector is going to be equal to 3 over root 13, -2 over root 13. We're going to find our derivative, and the derivative for this one's really easy because both the factors are independent of one another with respect to the variables. So let's find f sub x, and f sub x is just a chain rule. So we have e to the x, the sine y stays exactly the same, or e to the negative x, excuse me, and then the derivative of negative x is -1. So that's going to be negative e to the minus x sine y for our derivative. Fy, derivative of sine, cosine, e to the minus x is like a 3 or a 5 or a pi or whatever your favorite number is. So just bring that down. All right? And then we're going to evaluate both of those at 0 pi thirds. All right? Both pretty easy. So this becomes minus e to the minus 0 sine pi thirds. Sine of pi thirds is root 3 over 2. And negative e to the minus 0 is negative 1. So this ends up being negative root 3 over 2. Right? For this one, for our fy, that's going to be e to the minus 0 cos of pi thirds. Cos of pi thirds is a half, e to the negative 0 is 1, and 1 times a half ultimately works out to be a half. And finally, our directional derivative, du, at the point 0 pi thirds, is going to be equal to the first component of our unit vector. All right, so that's 3 over root 13, times our derivative of f in the x direction, which is negative root 3 over 2, and then plus, so we have the derivative or the unit vector in the y direction, so that's negative 2 over root 13 times 1/2, which is our derivative in the y direction. Right? And we can simplify this just slightly. We have negative 3 roots of 3 from the product of these two. And then we have negative 2 from the product of the numerators in the second term. And then finally, 2 times root 13 is 2 roots of 13. Right? We could just leave it like that. If you wanted to rationalize it, you can. If you want to factor out the negative, you can. All right, but this is probably a good enough answer for us. Okay, so hopefully this illustrates how to finish up finding directional derivatives. And again, remember, this is just a rate of change at a point in a specific direction. All right, and the direction can either be in the direction of a vector, or it can be in the direction of an angle, as we saw earlier.